I am going to do the post-contest stream for Codeforces round 698. So I'm still getting set up here. I actually competed in the Division 1 version of this contest, so I'm still working through the Div 2 problems, but hopefully I should be done before the scheduled stream time, which is, I think I set it for 8:55. Let me double check that. Yeah, I still have 3 minutes to solve B and C. Putting a bit of time pressure on myself, but it's okay if I don't finish. I can always kind of do it live. I think maybe people would like that too. But since I do have some time here, I'm gonna try to code up A, B, and C. Okay, let's just get my windows laid out correctly, zoom in a bunch. How's this looking? Okay, problem statements. Okay, position myself correctly. Alright, and let me also get my Twitch chat open so I can respond to any messages that come my way. Hey everyone, welcome to the stream. Anubhav, PowerSQ, iHeb, Habubi, Vamshi. My audio's a bit low. It's interesting. Let me see if I can fix that. Mr. Aurora, let me know, everyone, if my audio's a bit low or anything. I'll try to fix it. I want to know if it's happening for everyone or just some. Aha, maybe it's because I moved closer to my microphone. Yeah, so I'm just gonna wait another like maybe 5 minutes so that I have some time to prepare, but also so that people can trickle in. In the meantime, feel free to just hang out and chat, talk about how you did, discuss the problems, if you like them or not. Yeah, I personally thought the contest was good. I'm kicking myself for making some silly bugs that I only caught in the last minute. Fortunately, I did find them in the end, but would have rather found them earlier. Yeah. So I'm just typing up my solutions so that I can talk about them lucidly later on. Hey everyone, welcome to the stream. I'm solving them live because I didn't actually do these problems in the contest, but I figured, you know, Div 2 problems I can probably handle. And I'm not gonna have 100% confidence for any of these, but hopefully that's okay. But yeah, it seems like we got around 30 people on stream. I'll get started with A. And feel free to post any questions in chat. I'll be going through these problems at a medium pace. I'm gonna target something like around 5 to 10 minutes per problem. But if you want me to go faster or slower, do let me know, and I can definitely adjust. So, let's start with problem A. Problem A, I'm assuming you all read the problem, so I won't spend too much time reading the statement again. But to summarize, you're given an array of numbers, and they form a non-decreasing sequence. You want to color the numbers in this sequence so that within every color, those numbers of that color form a strictly increasing sequence. So strictly increasing is the condition we want to satisfy, but the precondition is, sorry, let me move my camera. You're right, I'm gonna turn off my light. Be right back. Okay, so I'm back. The precondition that we're given is that it's non-decreasing. So it might be equal at points, but it's never gonna decrease. So let's write some examples here. So in a sample, we have 1, 1, 1, 2, 3, 4. This is non-decreasing. And we want to split this into basically different subsequences that combine to form the original array. And the answer here is going to be split it into 1, 2, 3, 4, 1, and 1. So in this case, the answer is 3. 3 subsequences. And yeah, I can make the text a bit bigger. Thanks for the reminder. How's this? So yeah, this problem is just pretty straightforward once you realize that it's actually non-decreasing, because that means the minimum number of ways to partition it is we just, for everything that's equal, like every consecutive sequence of equal numbers, they have to be colored differently. And if you can do that, then everything else is going to be sorted automatically. So, solution, count the maximum number of consecutive equal elements in the array. So, yeah, I can make this even bigger. Font size. Yeah, I have to get used to seeing my code on a screen. Alright, so yeah, the solution is just to count the maximum number of consecutive equal elements. And we're actually given a nice constraint, which is that all of our numbers are less than n. So less than 100, which means we can just maintain a frequency array so that every time we see an element of v of our input, we increment the corresponding index in our frequency array. And then this is how I implemented it. I read in the array, I computed the counts, and then I took the maximum element of the counts. And there's a trick to take maximum elements, fix the title. Doing that right now. Thanks, Neil, for the reminder. I always forget to fix the title. Yeah, so that is how problem A works. I'm going to move on to problem B if there's no questions, but I'll give maybe another 15 seconds, 20 seconds, in case anyone has last minute questions. Why does counting the max work? Well, it's necessary and sufficient. Necessary because if there's 10 repetitions of the same number x, they can't go in the same array. No two of them can go in the same array. So you have to have at least 10 in that example. And sufficient because you're guaranteed that if you, I guess, do it this way, within every array, all the numbers are distinct, and if they're distinct, they're strictly increasing. Yeah, you can use map. If you didn't have the n less than 100 condition, you could have used map to do a similar frequency count. You could also take advantage of the fact that they're already together, or sort them. There's a lot of ways to count this. Why would the optimal order not? Well, I don't even. Yeah, their coloring assignment isn't necessarily like the same one we have. They just provide one of many possible optimal answers. There's not a unique optimal coloring, but ours like is an optimal solution. Yeah, the sample outputs are rarely gonna be direct hints to what your solution should look like. Like they're not easily generalizable, basically. All right, so I'm gonna move on to problem B. Sorry, is there something else I haven't noticed? Crow, refresh. What do I have to refresh? Oh no. Something. Am I missing something? Okay, whatever. I'm gonna move on to problem B. Don't tell me. Yeah, I am a beginner streamer, that's true. I'm sure there's something dumb I'm doing right now. Oh, isn't my face is too big? Okay, let me fix my face. How's that? Something else? Is it the fact that did I fail problem A or something? That'd be sad. All right. Let's talk about problem B, Nazar and lucky number. So this problem is actually kind of tricky. Let's go through the problem statement. I think I'm going to zoom out a bit. So yeah, Nazar has a favorite digit between 1 and 9 called D. And then he defines a positive integer to be lucky if D is present in its decimal representation. And then he has Q queries, where Q is like up to 10,000. And for each query, he wants to know if that number can be represented as a sum of lucky numbers. So one or more lucky numbers. And that's an interesting question, because lucky numbers are obviously like not too structured. They're not like all multiples of D or anything. They are just kind of random. Base 10 has nothing, like very little number theoretic significance. So what we can do is try to make some insights, which is like, one insight is you can always just keep adding D, because D itself is a lucky number. You can just add D over and over, and that means if you can make, for example, 10, you can make 10 plus any multiple of D. So yeah, that's one observation. So basically you can solve this problem modulo D. And let me actually start typing this out, because I think people will have an easier time following along. So observation 1. Because D itself is lucky, then if you can make K, you can make K plus any multiple of D. So we want to approach a problem, formulate the problem as, for every I modulo D, what is the minimum X I mod D, where X mod D equals I, such that X can be written as a sum of lucky numbers. So let me reframe this to be 0 I D. So yeah, that is I think the first step is frame the problem as a question that is independent of the query. This makes this question is independent of the 10 to the 4 queries. It can be computed offline, like pre-processing. And this will help us deal with the fact that there are tons of queries. It'll make oh, can't see what I wrote. Let me resize this. Thanks for the tip. Okay, how's that? Yeah, this is managing OBS for Twitch streaming is actually much harder than Codeforces sometimes, and that's okay. Okay, so yeah, let me restate that. Oh, Neil Wu subscribed. Wow, thank you, Neil, for the sub, my first sub. I'm sorry for not noticing that earlier. Yeah, I finally noticed. Thank you so much, Neil. It means a lot. Repeat observation 1, sure thing. So the first observation is that D is lucky. For example, in the sample case, what is the sample case? D is equal to 7, so 7 is a lucky number. So 7 is lucky. So if you can make x, you can make x plus 7 and x plus 14, x is 21, etc. So we want to know for each of 0, I equals 0, 1, up to 6, what is the minimum x, where x mod 7 equals I, such that you can make x. And knowing this, if we are able to compute these numbers, we'll be able to answer the queries pretty easily. Does that make sense? That's observation 1. So observation 2, or this is like strategy for actually finding these key x values. This is just a traditional knapsack problem. Approach like a knapsack problem. So you can just like maintain an array for each number, whether it's possible to make this number or not. And then as we discover new lucky numbers, we'll just add it to every possible number that we've already found is makeable. So the implementation strategy here, have a vector of bool, or bit set if you're advanced, of makeable elements. So that's what I'm doing here. I call it my makeable array can. Ignore this stuff. So can is a 2-dimensional array because I want to compute this for every I from 1 to 9. So this is actually a D. I'll rename that appropriately. And then what we're doing is we're testing all the numbers from 0 to 100, and we're seeing if they are lucky. So check if J is lucky. This is what we're doing. We're taking the 2 digits of J and seeing if either equal to D. And if J is lucky, then we're going to want to update our makeable array. So let's rename V to makeable for legibility, readability. And we're saying, okay, for every k from 0 to max n, and we should be a bit more strict with our bounds here, we're going to update, we're going to apply the update. So this is if k is makeable, then k plus j is makeable. This is relax this condition with the below assignment. So yeah, this is how I approach the problem. I didn't really read how other people did it, but I think this is probably a very common approach. and then I didn't actually bother solving the rest of the problem, but hopefully this idea works. Yeah, Ayush, what does this do? X mod 7 equals I such that you can make X. So, to rephrase, there are, of all the makeable numbers, what is the smallest one that is I mod X? Congruent to I mod X. Yeah, share the second test case. Sure thing. So that is 10, 7. So this is still D equals 7. Let's actually just print out can 7. I didn't run this code yet, so hopefully nothing embarrassing happens here. And can 7, in theory, is just going to tell us, let me give it T. For each I, can 7I will tell you whether I is makeable when D equals 7. So, yeah, we can do, just read the queries in now. How does this work? Can XD, then cal, yes. Then there's no T, right? It's just, oh wait, how does this work? So we want to do, well, T minus minus, read in Q and D, and then we're going to print out yes. So here, we'll print out dx and can dx. And, oh, we want to say maybe if x is greater than 100, do x minus equals something. We have to make x smaller than 100. But since the sample case doesn't have that, let's go ahead and just run it. Sorry. Shouldn't have deleted that. Okay, so yeah, let me illustrate. Oh man, everything's wrong, but it's supposed to be printing out nodes, isn't it? Well, that's kind of embarrassing. It's because alright guys, give me a sec here. I'm sure we can figure this out. Alright. Here's a test. Who can find my bug the fastest? I printed this out earlier, right? So I have 0, 1, 2, 3, 4, 5, 6, 7. Alright. This seems reasonable enough. I don't know why my code is disagreeing with me, but I need an else statement. Aha! Thank you for finding my bug. Who wins the prize? Else. Nice. Yeah, there's a lot of people saying else. Alright, great job everyone. You've successfully, I guess, debugged my solution. Okay, so with the power of teamwork, we were able to solve that bug. Great job, chat. Now we're printing out the correct answer. So yeah, walking through the second example, well, when x equals, let's say 51, we notice that can 751 is, I don't know where it is, but it's probably a 1. So that's why we're printing out yes. Okay, and then we do the same for the rest. We just index directly into our pre-computed list of answers. Okay, and finally, let's address this question of why can we just compute the answers up to 100? Well, it's because if you look over here, I printed this out and look at the end. It's all ones, right? Like, there's a lot of ways you could approach this. You could prove it using math, or you could just print out your array. Like, if we just print out can, and then notice that for every D that matters, it ends in a bunch of ones. Like, look at all these ones. Everything converges to all ones very quickly in the first 100 numbers. So that's like the empirical way of explaining why we can do this. It's because there's so many ones. Mathematically, well, you can think like, let's take D equals 8, for example. You can do 80, 80, 81, 82, up to 87. And that will represent all the moduluses, possible mods, because they're all distinct mods, and there's 8 of them. And in general, this works for all D up to 9. So yeah, that's why 100 is the kind of the upper bound for the smallest D you can make. And that's why you can do something like while x greater than 100, subtract D. You don't actually want to do that because that's going to be slow. You'll have to use a bit more math to do that exercise for the viewer. How is this div2b? Yeah, newbie, that's a good question. I thought this was a bit harder than I expected for div2b. In general, all the problems, yeah, they're kind of harder than I would have thought would be appropriate, but only slightly, very slightly harder. And it might just be because I'm more tired than usual that everything felt harder. I'm not trying to say the problem setter didn't calibrate it correctly. I think it just personally felt harder. Can we access this video after the stream? Yes, for sure. I'll upload this to YouTube right afterwards. Yeah, so let's move on to the next problem in a few seconds. I'll answer any more last minute questions in the chat. Trying to scroll through to see if anyone's reminding me for anything. Yeah, a lot of questions about Max and YouTube channel name. It's in my Twitch about. I'll paste it in the chat as well. If I can find it. I don't actually know my YouTube channel by heart, so I have to look it up. Alright, we can all spam my YouTube. Okay, yeah. Dio Hero, how did you think of this during the contest? How do we approach it this way? Yeah, I think observation 1 is pretty, I guess once you've seen this trick before, you'll be on the lookout for it. But in general, you want to, when you have tons of possibilities, there's tons of lucky numbers, but one of the lucky numbers is the easiest to reason about, and that is just the smallest one. So start with the smallest one, and then use that to kind of narrow down the problem statement. Otherwise there's just too much going on, too many possibilities of what we can do. We actually want to make the problem a bit more confined, arguably harder, but not much harder. Time complexity of my code in B. Oh, that's a good question. That's a really good question. So there's 2 steps, pre-computation and handling queries. The queries, it's O of 1, because for every x, all we have to do is index into a 2-dimensional vector. So that's very fast. And then the pre-computation time, we can count the for loops. So this takes 9 iterations. This takes 100 iterations, and this takes another 100. So total, 9 times 100 times 100, which is about 10 to the 5 iterations. And that's pretty comfortably within the time limit. You can usually do 10 to the 8. So yeah, that's the time complexity. What are the other questions? In my master on Codeforces, I'm red. I didn't do the div 2, but I read the problems afterwards, just so I could help explain them. All right. Yeah, there's probably faster solutions. You should if you need constant factors, you can use bitset. So tip advanced div 1, useful for div 1 only. Use bitset plus avx2 to get 1000x speed up doing these knapsack-like computations. There's probably a tutorial out there. Search Codeforces bitset. You'll probably find a good tutorial. All right, why do we run it 100 times? Yeah, so let me walk through this solution just one more time. We're trying to compute this makeable array. We want makeable to be a Boolean array such that if you index into it with a number I, it tells you whether I is makeable or not. We're going to initialize it so that only 0 is makeable. We're going to kind of relax the problem definition so that you can add 0 or more numbers. So 0 is makeable. They're not going to ask us about 0 anyway, so we can kind of decide for ourselves how we want to think about it. So yeah, in the beginning, only 0 is makeable. And all we have to do now is every time we find a new lucky number, incorporate that data, that information, into our makeable array. And the way we do that is we iterate through all the numbers, j and k. We iterate over all j to find all the lucky numbers. Once we found the lucky j, then we iterate over all k in increasing order. And this is important. We have to iterate in increasing order here so that we automatically get multiples of j. If k is makeable, for example, we're going to set k plus j to makeable. And then later, k is actually going to keep incrementing and get to k plus j, the original k plus j. And then it'll just keep going and get all the multiples of j. So that's why we do this 100 times. And that's why we do this 100 times. You have to check all the 2-digit numbers. What time is it now? It's like 9:20 a.m. All right. Let's move on to the next problem. Problem C. And let me know in the chat if you solved this problem, if there's any reason for me to be concerned, because I haven't read this problem yet and I'm about to explain it. Oh yeah, Neil Wu, that's a good point. It's a very good point. Not as good for knapsack because you can take things with repetition. Okay, chat, we're gonna solve problem C together. Let's start by reading the problem. Nazar and symmetric array. Long ago, there was a symmetric array consisting of 2n distinct integers. It's symmetric because it's the same. What is this? An array is symmetric if for every position in the array, there's another position in the array such that the values are opposites, as in one is the negative of the other. Okay, interesting. And they might be the same if, it's 0. Oh, yeah, distinct, okay. And then for each position, Nazar wrote down an integer d corresponding to the sum of absolute differences in I to all integers in I. Okay, cool. And now a million years have passed and he can't remember the array D and totally forgot A. Oh, he can remember D, sure, but he can't remember A. Alright, that's an interesting problem statement. It's a very, I've never seen this symmetric thing, but it seems workable. And then, okay, 10 to the 5 for everything, and the numbers are big. Sure. And yeah, just a reminder to everyone, I might not actually solve this problem very quickly, but let's see where we get. I think I should be able to figure it out just based on the fact that it's a div2c, but it might take me a few minutes. So yeah, let's look at the example. So the first array, we have D. Let's start typing our notes. Okay. Let's see. Example 1. We have 8, 12, 8, 12, and this is D. And we want to find an A such that, D is the set of differences. So one thing we notice is this is going to be xy, xy. This order doesn't matter when computing D. So that means if, if one value of like di equals dj implies ai equals aj. So maybe this isn't true. It's the other way around. It's not really if and only if. Okay. And then these are all distinct, actually. Actually, A is all distinct. So never mind. AI is never AJ. Forgot about that condition already. Okay, but the order doesn't matter. So we can kind of sort D, or think of D as a set. D is a set. Yeah, A is not this. I have no idea what A is yet, but let's see. Maybe we can just look at the examples and see what they say. 1, -3, -1, 3. Because the sums, the differences are 0, 4, 2, 2 equals 8. For the first one, 4, 0, 2, 6 is 12 for the second one, and symmetric for the rest. Okay, let's think about what happens when we sort this array. So let's actually look at A equals -3, 1, 1, 3. When we move from one to the next, how do the absolute differences change? I think it changes in a pretty predictable way. D equals, it starts at 12, and then it goes to 8. So D0 equals 8. D1 equals, it's just going to be D0 plus, this is A1 minus A0 times 1, and this is because it's 2 minus 1. And in general, DI is going to be, DI plus 1 is in general going to be DI plus AI plus 1 minus AI times absolute value of n minus 2I minus 1. Okay, or something. I don't know the exact. I don't know the exact balance. Okay, how does that sound? I think this sounds pretty good. So what I've done here is I found a way to go from DI to DI plus 1 just by looking at the values of AI plus 1 and AI. So I've really localized the moving parts of this problem. Because, the way they defined it was every D depended on every single value of A, but now I've made it so it only depends on 3 values. The previous D, the A's, and this is because we're sorting the array. So when sorted, we have niceness. We have a nice update formula. Okay, and this should help us a lot. Let me read the chat for a sec. Tell me if I'm on the right track, guys, if you guys solve this problem. You did the same thing? Okay. Well, now I'm thinking about it a bit more. This doesn't need the absolute value. So basically, reorder, like D must be a mountain, and consecutive Ds oh yeah, also, so translation of A, like A minus X for all I, does not affect D, so the log we can assume A0, 0. So yeah. Oh no, I forgot it's symmetric. Oh, I totally forgot to use that condition. Oh, and A is symmetric. Okay, let's think about how do we use the symmetric condition. Oh, actually, yeah, the symmetric condition makes the formula much easier. This makes D much easier to reason about. Because in general, let's say we have negative 10, negative 8, 3, 3, 8, 10. The values are really straightforward. Okay, yeah, this is the easier way. So ignore this part. The values are really straightforward to compute. Because let's say we're taking D2 equals sum of abs differences for, let's say, negative 3. Then we just do something like negative 3 minus negative 10. And let's actually pair that with negative 3 minus 10. So we're taking the difference, the distance from 3 to negative 10, or negative 3 to negative 10. And this is actually just going to be the distance from 10 to negative 10. In other words, distance from AB plus BC equals AC if B is between A and C on a number line. So this is observation 2. And this, what is the distance AB plus BC if B is not between A and C? It is, it's something else. It is something else. I think it's the distance to the closer one of them. But we can probably work with, it is more than AC. Let's say that for now, to say the least. So we can actually sort. So this observation gives us a lot. Scrolling up. So yeah, this observation actually solves most of the problem. It gets us probably 90% of the way towards a full solution. Basically, D is guaranteed to come in pairs, as in pairs. So we can sort it and look at even indices. So let's say we have 8, 8, 12, 12. Let's look at 8 and 12. Because, why do we sort it? It's because of this observation that if we start from the inside of A and go out, as in we sort A and look at the inside values first, these will have the smallest differences. Because negative 8 will be like 20 plus 16 plus something bigger than 6 when you take its differences to every pair. So the first, we can look at like the first value of D, even, is the sum of A positive. The second value of D even. So this is like an example case. So example, let's do 8, 8, 12, 12 again. And our solution was 1, negative 1, 1, 3. 8 equals 2 times 1 plus 3. Okay, so it is 2 times somebody positive. The second value of d even is oh, it's just 2a. That's right, it's the distance to 0. 2 times some is just d even 0 plus a0, a1, etc. So this gives us a formula to compute all values of a. Yeah, so I guess it is more than safe. It's 2 times a, because midpoint of BC is origin. Okay, great. So finally, let's talk about implementation. Let's turn this into an actual solution. I think what we want to do, well, I'm looking at the sample test case. I'm trying to understand it a bit more. 1, 4, go to 3, distance. Oh, I see. So it's plus a1 minus a0. So it's basically saying that the values of d, so let d equals vector in n, all the even values of d. So let's first validate that, okay, let's call this e, is in pairs. So this is like d times 2 times I equals d 2 times I plus 1 for all I and 0 n. 2, we define the half. Let's just call it half d. So we take all the even indices of d. And then 3, we start computing the values of a. So the way we do that is, let's do a equals zeros, then do ai plus 1 equals ai plus d I plus 1, or this is half d plus 1 minus half di divided by 2. There's an echo. Let me close some stuff, some windows. Yeah, so we use the observation that the differences in D tell us the differences in A. Yeah. Well, actually, we can directly come up with a formula. We can directly come up with a formula. I think it's just di divided by 2, or maybe it's divided by 4. 4, 6 minus 3. We know something about the sum of A. Aha. You're absolutely right. So we can do a of n minus 1 is going to be half d n minus 1 over 2 divided by n. And then a n minus 2 equals that divided by 2 minus n minus 1. So, sorry, half d n minus 2 minus n minus 1. Maybe I want to divide by 2 first. Okay, so let me write down what I read in chat. Serendipity, that helped a lot. I'm going to highlight this. There's a trick, which is basically we write it out like this. So yeah, this basically tells us that we can directly compute the last value, because it's just going to be d divided by 2n, the last value of d divided by 2n. Then the second to last value is this thing divided by 2, and then subtract the values we already had, and then divided by n minus 1. And then we can just keep doing this in general. Like we can maintain a running sum basically. We're going to take this minus like sum of already determined a values divided by minus 1, a minus n minus I plus 1. And this, and then we just have to cover, and then we just have to make sure all the divisions here result in integers. So check the mod before forming the division, and set ans equals no if mod is not 0. Akshat, nice to see you. So yeah, that might have not been the most concise explanation of this problem. It was definitely a bit harder than I thought it was going to be, so sorry if you're hoping for a more coherent explanation. But to recap, the way we solve this problem is we first make some mathematical observations. The observations that are most useful here are that once we sort D and we look at its distances, and this is really easy to see on paper, I guess, is if we're looking at the D with the largest absolute value, that is going to be equal to the sum of the A with the largest absolute value, that A's large distances to every other A. And if we pair the distances up, we can get that in a nice form. It turns out it's just n times the largest value of A, times 2. And then we can use that to get a similar formula to kind of compute the rest of the values of A. And this is like we have n linear equations, n variables. We can find them all using, in this case, a very easy Gaussian elimination. So yeah, to recap again, we do some math. We notice that on a number line, if we have x dot 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 x and then y minus negative x plus y minus x equals 2y. And that basically tells us we can find the value of the largest A because its distances, if you add them all up, distances for the largest A is just is just 2 times n times a. Second largest a is 2 times minus 1 times a plus 2 times, I guess this is like a, like 2. Plus a minus 1, like this. We get a formula relating the values of d to the values of a. We get a system of linear equations. Solve this system of linear equations by, eliminating / substituting in values that we already know. Great. AA tray, have div2, D, E, and F already been discussed? No, I'll do that now. Maybe I should have done that before C, because I actually solved D, E, and F. They were on the div 1. They are on the division 1 contest. Moving my face to the left side. All right, so yeah, let's talk about D. This one was also like surprisingly hard. This one took me a very long time to solve. We have n distinct integers written on the board. What we can do is replace, where we can add 2x minus y, given any pair of integers x and y. So you can think about that. This is a very common form. This is just reflection of x over y. So observation 1. X is reflection of x over y. And observation 2, like the previous problem, shifting everything, including k, by a constant will not change the problem, or will not change the answer. Because now that we know reflection, that is independent of a fixed reference frame. It doesn't matter where the origin is. And let's see. How did I end up solving this? Well, actually, before I explain the solution, let me see if my solution passed. Because if I failed, then it would be kind of sad. So, okay, my A passed. Okay, I can comfortably explain the solution. Reflection of y over x. Thank you. Yeah. I never figured it out on my head, but fortunately it didn't matter whether you're thinking about it x over y or y over x. Thank you. It's y over x. So yeah. One thing you can do then is reflecting a over b to a prime, then b over a prime to b prime results in, and we can draw this out, a, b, a prime, b prime. And these are all equidistant, results in b prime. And let's just call this a prime prime, because that's more apt. What have we accomplished here? What have we accomplished here? Okay, let me just say a prime, etc. You can generate all numbers congruent to a modulo b minus a. So yeah, basically, given a number a, you can reflect over another number and reflect to that number over that reflection and keep doing that to generate everything that's congruent to it modulo that number. So for example, if a equals for b equals 7, we can generate 10, 13, 16, etc. And also 1, -2, -5, etc. So yeah, I'm trying to find a closure of this, is it a group? Find of this like algebraic set of numbers under this operation. We're trying to find a closure under this operation. What did I mean that 2x minus y is the reflection of y over x? I mean that if you plot it on a number line, the distance from 2x minus y to x is equal to the distance from y to x. Distance, so y and 2x minus y are equidistant from x. The distances are x minus y in either case. Yeah, it's an arithmetic sequence, exactly. So yeah, we can basically take any two numbers in our sequence and extend them to form an infinite arithmetic sequence. That is the operation we have. Okay. What did I do next? I think I definitely overcomplicated the solution, but what I did, take the GCD of all differences, and then I did something kind of convoluted. I don't know whether or not it was necessary. Alright, give me a few seconds to rethink this. Yeah, I don't think I needed to do this 2 times g thing. Yeah. Forget all this 2 stuff. I think this probably would have passed. Now that I think about it some more. So maybe I should just submit just to make sure. I don't want to spread disinformation. Oh no, but I'm taking absolute values, so compilation error. Okay. I'm pretty sure that all you have to do is just see if you can. In the end, you're gonna have an arithmetic sequence, right? You're gonna have an arithmetic sequence that contains all your original numbers, and it's going to be the shortest arithmetic sequence, the one with the longest common difference. So let's just formulate this as observation 3. The set of numbers you can generate is the smallest, is the infinite arithmetic sequence that contains all input x with largest common difference. So this is the arithmetic sequence closure. I'll call this the arithmetic sequence closure of our input set x. And then once we know this arithmetic sequence, which is uniquely determined by its common difference g, it's easy to test if k is in the sequence or not. And implementation-wise, shift so that 0 is in x, allows us to work with absolute values without worrying, because sequence is now symmetric, borrowing definition from problem C. And then after we do that shift, compute G equals GCD of all values of X, absolute values. That is the largest common difference that you can get, is the greatest common divisor of all the values of X. Because if you consider a sequence, it contains X if and only if its common difference divides X. That's the value. That's why we want to center at 0. It makes it easier to think about that. And then test if, I guess K minus, just test if K is a multiple of G. So yeah, I could have simplified this a lot. Let's rewrite this. K mod G equals 0. Yes, otherwise no. I think that is all you have to do. And yeah, this will be uploaded to YouTube. Yes. So yeah, let me know if there are any questions about this. I think thinking about this as arithmetic sequences does make it a lot easier, because that is the structure of the problem. That is the structure contained within the definition of the operation of reflection. And this is not something I really had intuition for before. People in the chat kind of talked about arithmetic sequences a lot, but the flip operation generates arithmetic sequences. That is the essence of flipping, of reflection. And yeah, the set of numbers you can generate is necessarily an arithmetic sequence. It just is, because it's infinite, and you can't really overlap two infinite arithmetic sequences without adding new opportunities to flip. So if you consider the span, the closure, like all the numbers you can generate, it's going to be an arithmetic sequence, and it's the smallest one that contains everything, which you can compute using greatest common divisor. So yeah, it's a pretty elegant problem once we use all the mathematical observations and combine them. Implementation-wise, there's not much to it. I just read in the numbers, and took the first element, and called it offset. OFF is my variable name. It's the first element of V, subtract everything. And then now we know that 0 is in our set, and then we can just take the GCD and test if it divides K. Moving on to problem E. Problem E, I would say I was more comfortable with, and this one is a more traditional Codeforces problem. So quickly reading through the problem, which was actually really, I messed up when I first read the problem. I didn't fully understand it. But the way it works is Nazar has a string, and he has a friend, Nanako. Nanako will spend a few days inspecting the string to make sure that a segment of the string is all zeros or all ones. So Nako's gonna be like, okay, what is this substring? It has to be all zeros or all ones, or else he's gonna throw away the string. He's gonna rage quit. Now Nanako is able to, only after an inspection, change up to half of the characters in the string. So he's a sneaky one. He does this at night. He mutates the string. And yeah, at the end, Nazar is just wondering if it's possible to transform his string from S to F within these 2 days, while not pissing off Nanako. So yeah, he has a pretty difficult task. This is not something that, is usually, like, you wouldn't expect a random pair of strings and L and R to work. This is going to be deliberately handcrafted, but the way I approached this problem was first I misread it, and that really helped, by the way. First I misread it, and I thought Nanako got to change the characters first. I thought you got to mutate the string before inspection. So let me write this down here. So observation 1, misread the problem and think that you get to mutate the string before the inspection occurs. And observation 2 is there's always at most one way to mutate a string to be all zeros and all ones if you can only touch up to half the characters. 0 ways to do it if it's perfectly balanced, as all things should be. Otherwise, if there are more ones than zeros, you have to change it to a string with all ones. Likewise, more zeros than ones. Okay, so observation 2, let me know if that makes sense. This is with the misunderstanding that after your mutation, the inspection is going to occur, that you only have one choice. If there's more ones than zeros, you have to send the string to be all ones. There's no other option. And if there's equal numbers of zeros and ones, then tough luck. You cannot do it. There's just no way. And then observation 3 is like, once you're done, just make sure you've reached the target string. In observation 4, realize that the problem statement actually has inspection occur before mutation. But you can actually easily remedy this by reversing the order of everything. So you swap F, reverse L, reverse R, all is good. So yeah, observation 4, I would say, is the most tricky insight to make. And observation 1 is the most lucky insight to make. It's called wishful thinking. It's a technique known as wishful thinking. And this is often difficult to motivate if you don't see a clear path to reduction from problem A to problem B. But in this case, problem B sounded very solvable, and that motivated a search for the reduction. So yeah, problem B in this case is one where inspection occurs after mutation. So yeah, that's my that's how I thought about this. And then this is kind of the key insights you have to make. And once you've made these insights, it's just a matter of implementing this part of actually mutating the string and also determining what direction to mutate the string in. So the queries you have to support are determine if there's more ones than zeros versus equal number versus less. So that's 3 possibilities. You have to be able to query that, which are the 3 cases you're in. And then you have to be able to apply the update, where you update the string by replacing that substring with one with all ones or all zeros. And if you're experienced in doing data structures, you'll know that you can do this using a lazy seg tree, lazy propagation seg tree. I won't explain it in too much detail, but my code is on my Codeforces page if you want to read it. This is the code. It's pretty short for me. There's much shorter ways to write this for sure, but The key is basically I translated ones to I translated ones to positive 1, and where am I? Here. I translated the input into an array of 1s and negative 1s, and then you just have to query the sum, and then take the sign of that sum to determine kind of which of the 3 cases you're in. It's law of trichotomy. And yeah, you just do checks for every query, make sure that the sum is not equal to 0, and then do a check at the end to make sure you actually hit the target string, and then that's all you have to do. You just otherwise implement exactly as I tell you to do using the seg tree. Okay, so yeah, that's problem E. It's a pretty classic data structure problem with a small twist that you have to realize you can reverse things. Cool. And finally, let's talk about problem F. I'm going over problem F last, even though this was the first problem I solved. And this one is actually pretty sweet. So let's read the problem. Nazar, a nice beat map. He loves playing Osu. And that's an array of distinct points on a plane. The beat map is nice if no 3 consecutive points form an obtuse angle, or a right angle even. So yeah, he wants to reorder these endpoints now so that the resulting beat map is nice. Okay. If that makes sense to everyone, let's move on to the solution. So observation 1, 3 points determine a triangle. This is probably one of Euclid's postulates, but 3 points determine a triangle. Observation 2, the triangle has at most 1 right or obtuse angle. So in terms of this, ABC is invalid because angle ABC is 90. Then ACB and CAB are guaranteed to be valid 3-letter substrings. This is a rephrasing of observation 2, applying it to this problem in particular. So if we have 3 points and one of the orders doesn't work, then the other 2 orders are guaranteed to work. So solution now is just maintain a good ordering of the first k points, insert the k plus first point somewhere into this ordering, preserving its goodness. Nice. Sorry, it's called nice, not good. It's always possible among the k plus 1 possible insertion points to find one that produces no invalid 3-letter substrings. So here's my claim. And why? Because each invalid insertion point maps to at least one invalid 3-letter substring, but each invalid 3-letter substring, or invalid set of 3 letters, triangle, this is a triangle, can only be hit by one insertion point. So it's an injection. From insertion point to triangles is an injection. So that means that at least one insertion point maps to no triangles. Because there are k plus 1 insertion points and k minus 2 triangles, or k minus 1 triangles. So there are actually 2 possible insertion points, though we only need 1. So yeah, this is a pretty straightforward solution. We just try all of them. That is the answer. We just try all the insertion points, see if any of them work. The way I implemented this was I used this point library that I stole from the internet. This is from Cactal. Thank you, Keith Institution for Computing. I used Cactal. I defined this function OK, which given 3 points tells you if it forms an obtuse angle or not, using the dot product. Then I just had an array of points and I ran an insertion sort on it. It's not really sorting in this case, but it's the same pattern of loops. You just keep swapping your point of interest to the left until it's okay. And then you move on to the next point of interest, swap it to the left until it's okay. Do that for all the points. And then you're done. And then you just print everything out. I did swaps in lockstep on the actual array of points and an array of indices because I didn't want to like somehow make a pair of points and integers. That's too much work for me. So I just kind of maintained 2 different arrays in parallel, one of the values, one of the indices. That's ants, that's the values, that's the indices. And yeah, problem F, even now, I still feel like was the easiest problem of D, E, and F. Probably a minority opinion, judging by the solve times on these, but this one just felt much more natural than the rest of them. Because all you really have to do is like realize that there's no way they're going to make this problem that hard. There must be a way, there must be a trick somewhere that makes it actually really easy. And once you have that hope, then you know what you're looking for and you can make the observations you need. Can I let you know what's wrong with your solution? Yeah, let me take a look. You passed. Yeah, your solution is very similar to mine, except the problem is you might accidentally like consider DABC. Now you have DACB. DAC might be obtuse. So that's why you have to keep swapping until you reach a state where nothing is obtuse. So it's actually like an n squared solution, not O of n solution. Does that make sense? Yeah, but that's very close. That's very close to a correct solution. You just have to kind of replace an if statement with a while statement. But yeah, let's check the leaderboard and kind of review how the contest went overall. There are 7 people with perfect, or 8 people with perfect scores. Interesting. You have RNG59, a fan of RNG58, I assume. And yeah, it seems like the problems were a pretty appropriate difficulty if not too many people got perfect scores. Now check out the div 1. I'm not going to go over the problems because they were too hard for me. We had a lot of people with 5 problems solved, 3 of them, and then we had a bunch of people with 4 solves. Most of them solved problem D very fast, like Umnik, Bank, and Radowish. Though in 9th place, there's someone who solved problem E in the first like couple of hours or hour and a half. I had a lot of bugs on problem E. I swear, I would have gotten like top 10 if I didn't make so many bugs. Maybe not quite top 10, but I would have been up there. Yeah, I think I would have been top 10. Because like my first submission on E was at 126. Yeah, sure thing, Josh. I'll explain it once I finish kind of asking for pity. I had a bug here where I had an equal sign instead of a plus equal sign, and that cost me so much. So yeah, if I didn't make any bugs on problem E, I think I would have been top 10. But overall, I did pretty well. 38th place. That's probably plus rating for me, so I'm happy about that. Cool. So let's talk about problem B again. Over here, lucky numbers. Do you have any questions in particular about problem B? Oh, rating was updated? Oh, interesting. What's my rating? I got plus 34. Nice. Could have been more, but I'll take it. Thanks for the hint, everyone. That rating's updated. Hope you all gained a lot of rating today as well. So yeah, Nazar and lucky number. Here's my notes. How many years did it take me to get here? I started in high school, so that's like over 10 years ago. But yeah, problem B, the idea was basically you want to look at the problem modulo D. So for each modulo class, like 0, 1, 2, up to D minus 1, you want to find, like it suffices to find kind of the first value that is makeable with that given modulus. And that will allow you to really reduce the size of your input queries. The reason this modulus observation is helpful is we can take this 1 billion number and kind of drop it down to 100, at which point we can do a brute force like n squared solution of just using a knapsack style algorithm to compute this set of makeable numbers exactly. I can submit this code. Let me just fill in this. Make sure it's actually correct. There's a bit too much bug statements here. So I want a bunch of yeses, a few no's. Yeah, it looks correct. So yeah, I'll submit this code so that you guys can read my notes on my profile. Oh, okay, yeah, here we go. Submit problem B. And yeah, I hope that helped, Joshi. You can, oh. I got the wrong answer. This happens a lot to me, doesn't it? Where I'm explaining a problem, and I'm like, yep, I solved it, it's perfect, and then I end up getting wrong answer or something. Buffer overflow. Yeah, that's unfortunate. I don't know. I think I need to move this out of this statement. Resubmit. Yeah, thanks, Dash. Atray07. Do you want me to upload my script on GitHub that provides, let you submit a problem on Codeforces? Okay. I did not, I don't actually, my submit script doesn't do very much. All it does is it copies the file. I still have to use my mouse to click the button to submit. So I don't think you want it. Okay, I'm getting wrong answer. That sucks. I probably would have been better off not submitting. Now everyone knows that I'm a fraud. I'm a fraud. I'm sorry. I don't even know. I don't even know what's wrong here. Maybe this is. If it's 0, we want to subtract more than that. So maybe this needs to be 99. Submit it again. Add it off by 1. Just print yes for x greater than 100. You're a genius, Josh. Why didn't I do that? Yeah, I don't know why I thought that you just have to make x less than 100. Like, you can obviously just say it's going to be true. That's why this observation works. All right, accepted now. My honor has been restored. That's a good thing about solving problems online, is you can always get accepted eventually. Dash, you are a genius. You should be LGM. I don't know why Codeforces doesn't have you as LGM, but I think you have what it takes. All right, I think that's it for my stream today. I'm gonna go eat some food and go to work. But I hope you all enjoyed it. Thanks for tuning in. Thanks for all the support. I promise that I'll set up my stream to be more stuff like Streamlabs, Twitch commands with chat, like exclamation points and stuff. And that way you guys can get the links to my YouTube and submissions and everything without having to really work hard to search for it. Vim, yeah, Nightbot, I think that's something that I want to do. Am I streaming tomorrow? No, I don't think so. I think someone else is probably going to, though. Is anyone streaming tomorrow? No one yet. I'm sure someone will step up to the challenge, because it's good for the community, and I think people want to stream. What is my editor? This is Vim. Yeah, you can see up here, if you squint really hard, it says Vim a.cpp, the top left. What div2d? I'll explain it very quickly. Nazar and board. You want to find an infinite arithmetic sequence, and I might as well resubmit this. You want to find an infinite arithmetic sequence that contains all the points that are given. Does this compile? And you want to find the arithmetic sequence with the largest common difference. So yeah, ultra B. That was what I wrote in my notes here. It's like you first realize that you can take A and B to generate an arithmetic sequence by extending A and B. Oh, Pribic, am I studying or working anywhere? Sorry, I did miss that. I work at a company called Scale. It's in San Francisco, in the United States. Why isn't it letting me submit? I just want people to be able to see my code. D.cpp. Oh. Okay, yeah. And, okay, so back to the explanation. You find infinite arithmetic sequence with largest common difference that contains
the input elements, and then you just check if k is in this arithmetic sequence or not. The reason this works is because the set of numbers you can generate using the flip to reflect operation is going to be an infinite arithmetic sequence, and that means the smallest one that contains it is the one that generates it. And you can figure out what that arithmetic sequence is by taking the GCD of all the differences. Cool. That's it. Thanks everyone for tuning in. See you guys next time. I'll upload this video to YouTube. Yes, I will.